Okay, let's get started. Hello, everyone. Welcome back to our Distinguished Lecturer Series. So the Distinguished Lecturer Series here at the Max Planck Institute of the Science of Light is our most important event, bringing to you thought leaders in the world of the light. And we also welcome particularly guests joining us online. It's a great pleasure to introduce today's speaker, Douglas Stone from Yale. He's the Karl Morse Professor of Applied Physics and Professor of Physics at Yale, as well as the Deputy Head of the Yale Quantum Institute. So he has a very unusual career, at least at the start, certainly. So he studied social sciences at Harvard, and then he recognized at some point that maybe he's trending a little bit more towards the exact sciences, whereupon he then decided to go to Oxford, where he studied philosophy and physics, and then coming back to the States, he did his PhD at MIT. So he started out as a condensed matter theoretician. In particular, he's extremely well known for his theory of universal conductance fluctuations, where you study basically electronics in mesoscopic systems, which are larger than atomic scale, but smaller than bulk scale, and where, if you look at the electrical conductance, suddenly, unexpectedly, some universal features emerge. He made many other seminal, really important contributions to that field of electronic mesoscopic physics. But in the 90s, then having come to Yale as an assistant professor, he switched to optics. So he was the pioneer introducing wave chaos and ray chaos into optical systems, for example, looking at deformed microcavities, and then also applying to that newly developed laser theory, which he and his team developed in this setting, using techniques such as random matrix theory and generally tools of nonlinear dynamics and chaos. And based on these developments, he has also worked on what he will tell us about today, namely time reversing a laser. So we're really looking very much forward to that aspect as well. He has received numerous awards, including was a fellow of the Optical Society of America, and received the Willis Lamp Medal for Laser Science in 2015. But he also received the Phi Beta Kappa Science Book Award, and that is because he wrote a very interesting popular book about Einstein. It's called Einstein and the Quantum, The Quest of the Valiant Swabian. And I highly, highly recommend it to everyone here. Some of my PhD students have gotten it as a present already. So anyway, so I think that's enough for introduction. Thank you very much, Doug, for coming here, and we're looking very much forward to your talk.
Great. Thank you. I really appreciate the invitation. It's nice to learn about the exciting science that I heard about this morning and this afternoon being done here. It's nice to see a Yale postdoc graduate becoming a world leader in his field and reuniting with Florian. So, okay, so I'm going to tell you this story about time reversing a laser, which is, I think, very surprising that this feature that I'm going to point out and then generalize is something anybody could have noticed. I mean, they wouldn't have lasers till 1960, but you know, it's now 60 years later. It could have been noticed very early on, but it also revealed something so very deep that could have been realized many years. So really just a new set of concepts in linear optics of all wave equations. So it's an unappreciated symmetry of Maxwell's equations. It's a clue to a deeper structure in scattering theory, which applies to all linear wave equations, including the Schrödinger equation, as I'll show at the end. And I discovered this by accident while developing this thing we call steady state ab initio laser theory to describe weird lasers that didn't fit into textbook laser theory. So I want to mention my collaborators from the days of Coherent Perfect Absorption. That's Yidong Chong Li Ge, both faculty members now, and Wei Cao, my colleague. And then the newer stuff that's going to be the second half of the talk involves Wade Shui, also faculty member at USC, two of my PhD students, Will Sweeney, Ali Al-Hulemi, and recent collaborations with Philippe Hung and Michel Lin Sodi. So, okay. So let's review some laser principles, and maybe I'll find an excuse to get a little history in there too. I know many of you know about lasers. So a laser begins with an optical resonator and often just two mirrors, one of which is very highly reflective and the other of which is less reflective. And this optical resonator will have resonances, which in this case correspond to transmission resonances. And they can be characterized by the Q value and the finesse, which is the width of the line compared to the spacing of the resonances. And then to have a laser, you need to add a gain medium, which could be any atomic, molecular, solid medium with the right quantum material structure or molecular structure, and then pump energy in, which could be electrical or flash lamp or another laser in the modern era, or so on. And rather extraordinarily, as you pump harder, you get this very coherent, specific electromagnetic field pattern out, which is called a lasing mode. And this is what it looks like in some real life situation. Below when you're pumping more weakly, you just see a amplified spontaneous emission spectrum. And then as you pump harder, this narrow line, so the amplified spontaneous emission spectrum tells you more or less where the atomic or molecular transition is, but it's broad. And then you get this narrow coherent line out that may not even be at the center of where the ASE is, and this sharp uptick in the coherent output spectrum. So this is a self-organized system. You pump, the pump is not specific, it's not, I mean, there are all sorts of laser-like coherent light sources that are coherent, but the laser that was invented in 1960, you put energy in and it somehow converts it to a specific frequency, single mode usually when you get started, low entropy output of beautiful light. Okay. So the principle of the laser goes back to 1917. Einstein in 1915 had finished general relativity, and then just 9 months later he came up with these new ideas, but they didn't get published till 1917. That, by the way, is Einstein in 1905, in case you don't recognize it. So he developed the first principles that everybody here must know this, of the quantum theory of the laser, but it was just after Bohr had actually succeeded in doing the first quantized energy theory of the hydrogen atom, and so now he decided to do some kind of statistical argument about radiation. So imagine we have many identical atoms in the ground state, which is going to be our gain medium, okay, and if a photon comes in, it can be absorbed and create an excited state. And Einstein then said another thing can happen, maybe I'll put it back there, which is very strange, that without anything disturbing it, it can suddenly just fall down. Okay, and that, of course, is spontaneous emission. And this is the quantum effect. This did not exist in classical electromagnetism, and it's random. And Einstein in 1917 said that this was an issue for him. I'll come back to that in a minute. But imagine, again, that you have this excited electron and something does happen to it, meaning another coherent light source excites this atom, then it can do stimulated emission, which notice was faster, and send out another identical photon. Okay, so Einstein had to put in this new property of spontaneous emission to get the right Planck radiation law. And this is really the first statement that the new quantum theory was going to have uncaused events, that there was going to be intrinsic randomness. And of course, ultimately, Einstein didn't like that and didn't accept the final version of quantum mechanics. But at the time he wrote, the weakness of the theory lies in the fact that it leaves the time and direction of the elementary process to chance. Nevertheless, I have full confidence in the reliability of the course taken. Very interesting, because at that time he was very excited because it's such a beautiful derivation, but eventually he changed his mind. But stimulated emission, which comes into the laser, is actually a classical effect. It's the effect of external, a source driving an antenna, and Einstein was well aware of that. Now, another great physicist, Charles Townes, it took for like 40 years or more before the idea of creating a laser light source came about, and Townes gets a lot of the credit. And here the idea that you're again probably aware of is that if you pump energy into the medium to the point where you invert it and you have more atoms in the excited state than in the ground state, then when you send light through, you'll have stimulated emission, and you may have some absorption, but because it's inverted, the stimulated emission wins, and you get amplification. So that's amplification of the input light, light amplified by stimulated emission of radiation. But that's not what we usually refer to as a laser. These days, we refer to, I do want to say something, that the gain medium in its inverted state has an imaginary part to its index of refraction, which corresponds to negative absorption. So plus IN prime would be an absorbing medium, but minus IN prime is an amplifying medium, and it can never happen in thermal equilibrium, but it can happen when you pump a system here. So that'll come back, this negative imaginary part of the index of refraction. Okay, so that sounds like a laser, but it's not a laser yet, because we know that a laser is a light source, not just an amplifier, at least often that's how we use it. So now, instead of putting in a coherent light beam, imagine we put this in a resonator, and we start with spontaneous emission, and this bounces back and forth and causes stimulated emission. And if the amount of light that's generated in a round trip through stimulated emission inside the resonator is equal or greater than the amount that leaks out every time it bounces, then I can have an exponential growth, and the laser turns on as a bright light source. So you need the outcoupling loss to be less than or equal to the round trip gain, which you can express in this way, that the reflection times the growth in one round trip has to be greater than or equal to 1, and then that's how it self-organizes. And it self-organizes not in a random electromagnetic mode. If this atom had emitted in that direction, it would have had no feedback, and there would be no such process. So this actually finds the highest Q, highest gain mode of the field that's allowed, and that's how it first lases. Okay, so it's a very interesting natural self-organized oscillator. Okay, so that's a light oscillator by stimulated emission of radiation. And for some reason, they didn't choose this as the name for the modern thing. They just stuck with laser. I can't figure. Okay, so anyway, now, as I said, it took a number of years, and actually Townes finally demonstrated the ammonia maser in 1954, and he did it by looking at a certain quantum level of oscillation in the ammonia molecule, which was in the microwave. And he did this against the advice of his departmental chair, who thought he was wasting time and money. That happened to be I. Rabi, that some of you may have heard of. So anyway, and then Ted Maiman just demonstrated the Ruby laser in 1960. Townes got the Nobel Prize for his work in 64. This is what Towns looked like at age 94 with some other guy standing next to him. It was very exciting to meet him. Anyway, so the theory of the laser is not simple. It's nonlinear coupled partial differential equations coupling light and matter, and this is semi-classical theory. If you put in full quantum operators, then it's even worse. So it's not a really trivial thing, and so people did different aspects of it over the years, and certain aspects were not really addressed. But people kept inventing new and interesting lasers, and so there was some market for new laser theory. One of the really weird lasers, actually, I invented one, this chaotic laser, but I just mentioned the one by my colleague, Wei Cao, which is just a aggregate of nanoparticles with gain when you pump it, where there's no cavity at all. There's just this aggregate, and the light gets emitted, and it diffuses around and goes out. So nobody engineered anything. Nonetheless, if you pump hard enough, you get these narrow lines that came out of it. And having a cavity that isn't really a cavity and is random had not been considered before in laser theory. And it's sort of, I was coming from chaos and disordered systems, so natural to say, well, how can we explain this? Particularly, I won't go into it, but there were really weird, wrong ideas out there, which I knew were wrong. So another longer discussion. So what we wanted to start with was a general definition of lasing and a theory that might then answer some more detailed questions like how many and which modes lase for a given pump, what determines the frequency, is it a stable state, etc. So Maxwell's equations, as I said, the whole laser equations are complicated, but I'm not going to write those. Below threshold, before it starts to lase, I can just think of a Maxwell equation in a completely general geometry. So I can say there's some place that I'm going to call the cavity, which with some linear dielectric function that cannot amplify and let's say is lossless, that would be maybe my random scattering medium. And then there's a gain medium of some atomic type in there as well that's going to give us the lasing. I'm going to look for a harmonic solution of the equation, and I'll get this kind of Helmholtz-like equation, slightly simplifying, ignoring vector nature and so on. So in addition to the epsilon cavity, I have this chi gain, which is the additional susceptibility due to the gain medium, and it's going to have a negative imaginary part when I have an inverted medium. Okay, and so the equations of the inverted atoms give the gain susceptibility, and it will be nonlinear above threshold, but below threshold I can just treat it as somebody gave me a negative susceptibility. I don't have to write those equations yet. Okay, but what are the boundary conditions on solving this wave equation? Well, it's a source, so it's going to be purely outgoing boundary conditions, right? And this is not necessarily the usual these are not the usual boundary conditions for solving wave equations. When you have this kind of boundary condition, the solutions are discrete. So we're all familiar with the fact that when I write this Schrödinger equation, that we in steady state, that E is the eigenvalue that we want to solve for. And similarly, when I write this wave equation, that now I'll only find solutions for discrete omegas, which we're going to talk quite a bit more about. Okay, but omega I should be real, because it's a harmonic, real, steady state output. Okay. Well, there's something many of you may know about, or have learned about, hopefully, a bit, which are resonances of a passive system. So this is, again, some region that can be the cavity, but we don't have any gain medium, so it's not really a source. But we still insist on looking at purely outgoing solutions, okay? So every system like this has scattering resonances at discrete complex omega. okay, where the imaginary part has to do with the width of the resonance, this imaginary part of omega, but unfortunately it makes the spatial part go to infinity when you let the radius go to infinity. So it's not actually a physically realizable solution, but it tells you something about scattering. It tells you about the normal modes of the system and the places where waves constructively interfere inside. Those are often called quasi-normal modes or various other terms like that. Now, if the dielectric function here is real, then the omega I must be complex because there's no source for the actual photons, right? So they'll have to be off the real axis solutions which are not physical. Okay, so there one is. It's below, it turns out it has to be below the real axis, negative imaginary part. But now when I add gain, and that means I have a complex part here, which represents the source of photons from the atomic medium, I can actually get the frequency to become real. Okay, and now I have a steady state linear solution of Maxwell's equations, which is purely outgoing, which is great, except you have to notice that you also have a infinite response. So if you put even a tiny bit of light into such a system in linear response, you would get infinity. So you immediately have to add. Well, there it is. It's out. It's emitting, but you have to stabilize this by adding the nonlinear effect of saturation. And if I were talking to you about steady state ab initio laser theory, that would be a lot of the rest of the talk. But I'm just saying that's going to have to happen, but we're not going to talk about it. This is linear. Everything's linear. So the purely outgoing states of the passive system without gain, I don't even know why that was there now. I think that should have been up one. Sorry, that should have been an introductory slide to the previous one. So this idea of taking a resonance and making it, making it real, that is your general definition of the onset of lasing, which a few people, I think, knew this before we emphasized it, but really it was very rarely spoken about. So I'd be curious if anybody knew this here or if people learned this in their class. I don't think it's usually taught. But I definitely know people that knew it. They say, oh, of course. But anyway, this, of course, gave us a way to define the threshold for lasing without having anything like reflection coefficients. This is some chaotic shaped D cavity that we actually made a laser out of. And this is some resonance for that laser. It's provably chaotic for the rays, etc. Here are all the resonances, and we added gain, and one of them reached the real axis. And even though we don't have any criterion like R times E to the blah, blah, blah is 1, this is the criterion for lasing. Okay, so this is rigorous meaning. Now, a second example, which I want to show you, is just a random laser where I have a gain particle that's sub-wavelength, but very strong, unrealistically strong gain. And then we just solve this numerically, and whoops, it moved. So let's see if I can. All right, well, this is, I think I'll just go out and fix it. I didn't put it back. No. All right, so this is it. All right. Okay, so this again is a calculation where you have this sub-wavelength gain, but it's very strong and it randomly lases and it looks pretty cool. So I wanted you to see it. Now, so it's self-organized, and you can kind of look at this wave, this very weird distorted wavefront, right? That is the thing that optimized the Q of the cavity, and it lases. And it's really a sample-specific adapted waveform. So could we use this? I mean, it's pretty amazing, this waveform, if you like. Okay. So, of course, the obvious thing to us, to me, was, well, maybe I could think about the time reverse of this, where instead of saying I'm looking for purely outgoing solutions, I look for purely incoming solutions. Okay. And this is just the complex conjugate of outgoing. So if I complex conjugate the wave equation, I'm going to look at a complex conjugate frequency. Remember, frequencies can be complex here. And I'm going to complex conjugate the susceptibility so that negative I gamma becomes plus I gamma. That's normal absorption. So in fact, here in this inside, I've replaced gain with the same level of absorption everywhere. I've got an E here. It should be, E is, yeah, that's fine. And the electric field has been phase conjugated, so that means it's incoming. Okay, so that's what I just said. And then because everything's complex conjugated, this is a solution, and it's just the complex conjugate of the resonance solution if there's no other, if there is no if there's no gain in the system. If I just get rid of that, if there's no gain. If there is gain, then, as I said, gain gets turned into loss here. And if chi gain is tuned to be at the lasing threshold, then the zero will, this absorbing mode will occur at exactly the same frequency. So we have perfect absorption for the time reverse of the lasing mode at omega lase, because when it's real, omega star and omega are the same frequency. So that's coherent perfect absorption or time reversed lasing. So it's a property of the laser equation at threshold that just nobody had pointed out, as far as we know or noticed. So there it is. Okay? Now, one interesting thing is the laser optimizes. So if you pump the laser, it's going to pick the mode for you. But if you put in absorption, you could do this for any resonance. So you can actually, you have much more freedom to make a perfect absorber with a resonance that would never lase. So in that way, but of course it's very hard to send that wavefront in. Okay, so as I said, it's an unappreciated symmetry. If you do this complex conjugation, you get perfect absorption of the time reverse of the lasing mode, i.e. for the case I just showed you for that really weird outgoing waveform, just conjugate it, and that somehow finds its way through. I'll show you that in a minute. Okay, so we wrote this paper back in 2010, and I want to just make a few physics comments about this. There's no enhancement of material absorption here. What we really made is an interference trap for light. So that you send in this adapted waveform, it's perfectly adapted, so it can't get out, and then it just rattles around, and because there is some absorption, it all ends up getting perfectly absorbed. So we didn't enhance absorption here. We made a one-way trapdoor for light. Okay? And time reversal is only applied to the wave equation, not to the matter. Different things are happening in the gain medium than the time reverse of what happens in the laser. So this is a form of perfect impedance matching, but only for an adapted waveform and only for transduction. Okay, when we talk about impedance matching, sometimes we mean something more general. But here, everything is transduced because the thing that's making it happen is the matter's susceptibility here. So often in optics, we don't distinguish between scattering loss and material loss, but this chi is representing an irreversible process into a reservoir, and therefore it's transduction, not, okay, all right. Now I'd say that an important case of this was known for at least 75 years and maybe more, not connected to lasing. It's sometimes called critical coupling. And one example of this, which was done in the 80s and early 90s for potential optical computing, was this critically coupled asymmetric Fabry-Perot resonator, which in a cartoon form has a perfect mirror here, and it has an input mirror here, and they use the electro-optic effect to change the absorption in here. But if they tune the absorption to the right amount, then they got this property that the reflection from the back mirror and the front mirror destructively interfered and everything was absorbed. David Miller at Stanford was on some of these papers, so on. Another example that's called critical coupling is the critically coupled ring resonator, which you see in silicon for photonics. You have a bus waveguide and a ring, and you send a wave on the bus, and if the coupling in and out equals the round trip loss coefficient, then you get nothing out. And here, it's not an irreversible process in the sense of transduction. Actually, it's mostly radiated, at least in silicon photonics. And so I'm going to come back to this other kind of reflectionless thing. In this case, it's transmissionless, but it's called critical coupling. So this thing here is really time reverse lasing. If I had a laser with gain, it would emit just out here. It's an example of CPA in the simplest possible way. The other thing is not, and I'll talk about that later. As far as I know, still to this day, I have not found a single reference where somebody referenced this kind of thing to lasing. When they did the calculation to prove that nothing came out, they just did the calculation. They could figure out how it would work. And I've already said the critically coupled ring is different because there's no transduction. And now we'll include both cases in a more general theory. This is radiative loss will be. Now, a simple non-trivial case where you could think about coherent perfect absorption is this balanced Fabry-Perot, not asymmetric. So equal mirrors and a weak absorber inside. And people had the idea that if you illuminated this on resonance, even if you have a weak absorber, you could have strong absorption because it stays around in there a long time. There's a high field intensity. So they played around with this, and they could barely get more than 50% absorption. And at the time, apparently, they didn't really have a reason why. But the reason why is that it's not the time reverse of lasing. Okay, this thing is symmetric. It would lase like that. So we have to send in two beams, phase coherently with the right phase difference, and then we should be able to get it all absorbed, be able to make this trap for light. So we did this experiment a year later we just had to find the right tunable medium. So we just used a silicon wafer that we could tune through the band gap so we could change the absorption very quickly, without changing anything else, and then put an interferometric setup here and measure the reflected stuff in both directions. So we're illuminating it from both sides. And the theory says that there, at some frequency, one of the modes will be perfectly absorbed, the other will be strongly scattered, and they'll be odd and even, and then they'll change their role. And in between, the in-between isn't not there, but anyway. Okay, so we did the experiment, and this is pretty good. This is, like 98% absorption. And if we change the frequency, then it doesn't go down to zero like I've shown here. And we looked for a point where it was insensitive to the phase, which should exist. They didn't find it in this experiment, but it was decent. So, okay, and this came out in Science, which gets even more attention than PRL. And so the Yale Public Relations Office wanted to talk, write something about this, put out a press release, and they said, we don't like coherent perfect absorber. Okay, you have to call it something else. So I said, call it the anti-laser. Well, I don't know if it was a good or bad idea, but it did catch on. Okay, so I don't know, this was a while ago, but if you Google anti-laser in Yale, you get, 1.5 million hits, and it was covered in a lot of places, like the New York Times, and even Fox News. And I'm sure you can imagine how excited I was to be covered by Fox News. So this is how they covered it. Dear James Bond, next time a laser beam threatens to cut you in two, switch it into reverse. That's Fox News for you. Okay. So that was fun. Okay, so let's go back to my exciting, remember the random laser with the very high gain? Well, now let's put in a very lossy particle. Let's send in the time reverse, and this is, you know, this is cool, and it just looks cool. So the point is that these are all scatterers. Everything here is lossless. The only thing it can absorb is that. And these are shielding this lossy particle. So, is it actually possible to find a way to get the waves all to go through there without scattering and be fully absorbed? And the answer is no. Usually there isn't. The theory tells us that unless you do tuning, you won't be able to find that wavefront. You need to find the right amount of absorption, the right frequency. Okay, but it always exists. So if you know it's there, you can tune to find it. And this is really non-trivial. I think most physicists would say there is never a solution of this kind. Okay, so something like this was done in a microwave setup that involved my former postdoc, Stefan Rother, and other people. And here they have, this is their random scatterers. There's 8 different antennas at the outside. Let me see, I think I have this animated. There's a central antenna, which is like my point-like absorber in the thing on the left. And they want to find their way through the scatterers to do this. And they were able to do it. You have to send in a coherent signal in all 8 antennas that exactly interferes correctly to do this. And then they also sent it back. So the blue here is when they correctly tune the 8 inputs, and the red is when they send the signal back through the single central antenna. But the fact that it sort of worked in time reverse means that it's not CPA because they didn't replace gain and loss, right? So this is something else that looks like CPA. They called it random anti-lasing. It shows that something like this can happen, but the something is actually something slightly different. Okay, and they showed it was sensitive to the relative phases of the antennas and so on. As I said, it's not exactly CPA because there's not real transduction here. Okay, so, all right, well, any questions? Yeah.
So I have a question. So in case of lasing, you at some point have some sort of saturation, because otherwise, is there some similar thing here, so that at some point it gets transparent again?
Yes. So first thing is that, so everything I've said is in linear response. So all my statements here, thank you for the question, are based on the assumption that we have a good enough heat sink that we can stay in the linear regime and we don't saturate the absorption, right? So of course, it's actually pretty easy, I shouldn't say that, but having done laser theory, it was easy to do saturable absorber theory. And my student, Will Sweeney, who's one of the co-authors on this work, that's part of his thesis. So what happens there then is either you saturate right away, so you get a tiny signal and then it stops perfectly absorbing, or you keep it below threshold, right? I mean, you actually are you're overcoupled, and then as your signal goes up, you saturate, and then the absorption reduces, and then you go up to the real axis, and then at some finite place, you have perfect absorption, and then it goes away. So there's lots of nice stuff there. But definitely, most of the time, we're going to talk about linear response, where we assume the energy can be synced in some way. Yeah?
You emphasize a lot that it's not obvious, but for example, if we have a dipole, if you want to fully excite it, you need to have dipolar emission, dipolar excitation. So it's kind of obvious that if you want to have perfect excitation, you need to have the reverse of the emission.
Yeah, I don't think it's not a perfect analogy. The thing you've said has been noticed over and over again, right? So that's emission, say, of a photon from an atom, right? This is steady state, right? The laser is a medium, and it's a steady state sink. It's not time reversive emission, steady state. So, moreover, of course, dipole, we're in free space, and we're assuming, you know, that we have some spherical symmetry and so on. Here we don't have any symmetry, right? So the mode that's the time reverse of the laser emission is highly non-trivial.
I think that the symmetry doesn't matter. You just need to reverse it, and if you continuously drive it, you have a steady state. So
No. You know, if you time reverse it, it's going to go right through the antenna and come back out the other side. It's not going to be absorbed.
okay.
You know. And people have done these experiments. Yeah.
You talked about the
It will focus, but it won't unless you change the phase and everything. Yeah.
I want to ask about this asymmetry between laser and perfect absorption. So you said that laser like chooses the most high Q mode to laser in, but for the reversed, for the absorption, it is not the case. Where does this asymmetry come from?
Yeah. So the asymmetry comes from the fact that the self-organization is because you're trying to find the mode which is going to beat the loss, right? So it's just randomly trying, but there's one that beats first. Okay. When I'm coming from outside with with an input waveform, if I have to study the system to find out what that waveform should be, the laser will not tell me about a much worse resonance that doesn't turn on, right? So I have to calculate it. But if I calculate it, I can critically couple to any resonance. Yeah.
So where does this energy go? It absorbs and then what?
Yeah, so it's different for everything. So the chi absorption is whatever physics is relevant. In the silicon experiment, it was heat. And when the resonator was too thin, the heat kind of messed up the experiment. So we made a thicker resonator so that it could work. But it could also be incoherently re-emitted, or some other nonlinear process would count, because from the point of view, then it's still transduction, right? It's still some form of transduction. Okay. Thank you for the questions. So one thing that a colleague of mine, Philippe Delhune, thought of as an interesting thing would be to do this CPA thing in a microwave cavity with a kind of chaotic insert here, and with this thing called a metasurface, which is like a liquid crystal screen with some number of pixels, in this case 16. Okay, and 16 pixels, which can be have one of two settings, so there are 2 to the 16th different sort of scattering matrices associated with that thing, and so you can search for CPA by tuning this metasurface. Okay, and they easily found 60 dB of suppression corresponding to CPA. They have a lot of background loss even when it isn't at CPA. And then they found, I think, 8 different CPA configurations, and these are the settings of the 16 pixels that give you CPA, and then non-CPA doesn't have any of this, so on. And one of the ideas they had was that if Bob was trying to communicate with Alice, and Alice was controlling this programmable metasurface, that Alice could turn on and off the CPA configurations in each channel. Bob could just send in all these frequencies, and when he gets no reflection back, then he knows it's a 0, and when he gets reflection, it's a 1. So she could send messages to him, and if Eve was eavesdropping, there would be no CPA when Bob is measuring no reflection. Eve wouldn't know that information was being transferred. So they called it receiver-powered secure wireless communication. Also, I already said this. You could also use this for analog differentiation, which they did and demonstrated. Okay, so now let's get back to this point about reflectionless but not coherent perfect absorption. Okay, so remember in this case, I'm going to call this zero reflection when it comes in here and doesn't go through. In this geometry, this is the analog of reflection. Okay, but it just gets lost into radiative channels, which you could in principle time reverse if you measured them carefully. Okay, so it's not transduction, it's not in the chi. You wouldn't put it in the chi of the wave equation. Okay, and this is sort of like the microwave experiment that I said wasn't really CPA. So, but this is often what we actually care about. We want zero reflection, right? If it's radiative loss, that may be okay. So how can we generalize to include this case? And here we're going to now define a scattering matrix, which many of you may know about. So if I have some arbitrary system, epsilon of r, okay, what we would talk about, if it's finite, I can always make a set of incoming and outgoing channels. We'll assume they're time reverse of each other that scatter, and the rest don't scatter from this object. And so I can define a finite S matrix, okay? And if it tells me if I have amplitudes alpha 1 to n in each of the channels, what's going to come out in the time reverse channels. And it's a linear matrix that depends on frequency. And if I send the alpha 1 in only, then I get the output corresponding to the first column, and so on for the alpha 2, and so on. Okay, if I send nothing in, that's the case of resonance. That's going to be a pole of the scattering matrix, and it will have to be infinite to get something out. So that's kind of an unusual case. CPA is not as weird, right? I fill all the channels in general. I get nothing out because it's perfectly absorbed. Obviously, I don't have a unitary S matrix that conserves flux if that happens. Okay, but it's an eigenvector of the full S matrix with eigenvalue 0. Okay, so now I want to do a generalization. Also, similar things were done by these folks, not in the general case. So let's say I really just want these to be my input channels. I don't want anything to come back in these 3 channels, but I don't care whether they come out here or some is absorbed. Then I can write this input vector with only 3 components and all zeros, and I can insist on having all zeros in the first 3, and that will be a general definition of reflectionlessness for an arbitrary finite system, okay? But then I'm just looking for a 0 eigenvector of this 3 by 3 submatrix of the S matrix, okay? So I'm looking for a 0 eigenvector. We're going to call this R sub n for this particular choice, and there's some eigenvector maybe that does it, which is we're going to look for when the determinant of this is 0, and then such a vector exists. But it won't have a solution at all but discrete frequencies. So this is very similar to the coherent perfect absorber, where we just took the whole S matrix and looked for 0. Now we're looking for a submatrix. So the thing we had to prove is, does this also have discrete solutions, countably infinite, the way we have for resonances and zeros of the full S matrix? So we did show that. But it does have countably infinite discrete solutions, but there's a new complex spectrum for each impedance matching problem. In other words, if I choose these 3 to be the input or these 5, I have essentially 2 to the n minus 2 different impedance matching problems, not counting CPA and resonance, that we can now look at that have different complex spectra. And but it's only really reflectionless, just like for resonances and zeros, the imaginary part screws up the behavior of the solution at infinity. So if it isn't real, then it won't be a real steady state solution. Only when the frequency is real is it a steady state. And again, we'll be tuning the system in some way by varying a parameter to make a frequency of interest real, but we don't necessarily have to add loss or gain, right? for all outgoing or all incoming, we're violating conservation of photons, so we clearly have to add loss or gain to make it work. Here we do not. It's potentially doable with a lossless structure, in effect. And we're going to use the notation that if the frequency is real, we're going to call it a reflectionless scattering mode. This is like the laser, we call it a lasing mode. And if it's complex, we're going to call it an R0. Okay, so here's a calculation we did for a chaotic shaped cavity where we chose 3 input leads that we want to be reflectionless, and the other 3 are output leads. We calculate for actually different choices, and these are different choices of the boundary condition as shown here. Here are the resonances and zeros, but the reflectionless frequencies are not them. They're qualitatively different. And we've tuned it. None of them should have been real because there's no symmetry here, but we tuned it to have one of them be real. So that one we did a little tuning of the leads here to make them make this frequency be real. Okay, and then the others, none of them are real. Okay, so that's the reflectionless scattering mode. This is an open junction with low Q and transmission through multiple resonances. So this is a very, very hard problem to do without our methods. And people tried to do stuff like this, and it wasn't very useful. Okay, now to understand this better, let's do the same junction, but with pinched off leads or waveguides, so it's evanescent. So this is much higher Q. In this case, it sort of makes sense. You're only going through one high Q resonance, okay? And so now the spectra all line up. They have the same real part because they're all going through one resonance and just different imaginary parts. Still can be on the real axis, but it's not as surprising. And you can guess how you would excite this. Just start with the resonance, which I'm showing here, and just take 3 of the outputs, amplitude and phase, conjugate them, and that will give you the reflectionless mode. So for an isolated resonance, I don't know why people didn't know this, but it's pretty straightforward. It's some kind of phase conjugation. As soon as the resonances overlap, then you don't have any simple condition, and the example I gave on the previous page I claim is highly non-trivial. Okay, and you can see that it's non-trivial because unlike this, which is a single resonance, this is the RSM with it's just blinking on and off. This is going through multiple resonances, so it's doing some kind of rotation here, and it actually looks to the eye different. But you see it is reflectionless. You can see the traveling waves in the different leads. So once we had this idea, then we thought, well, wouldn't it be great to control this? So imagine we had one of those metasurfaces like we already saw on this cavity, okay, and maybe we could change what our boundary conditions were and find a reflectionless state. Maybe we could toggle between them. Maybe we could do it at 2 frequencies. Maybe we could do something really useful, okay, which is have it be reflectionless for frequency omega 1 and for frequency omega 2, but have the output only go into one of the desired ports. That's not guaranteed by the theory. You have to do some optimization to see if this is possible. But, okay, this would be a way to make, obviously, a demultiplexer, right? We did this with Philippe Delhune, similar kind of setup. I won't go through the details. 3 or 4 input ports, measure the scattering matrix, look at a submatrix, see how close it is to having a 0 eigenvalue, and search for that. Okay, and they were able to find, by searching, thousands of reflectionless modes, and they could target a specific frequency. So this was a reflectionless mode they found without targeting, and then they targeted 5.2 gigahertz, and they were able to get it to happen where they wanted it. But then they tried to do this more complicated, challenging thing called a demultiplexer, okay, where you do exactly what I said, that you have 2 signals at different frequencies and you drop them in different ports. So they optimized it, they measured a lot of S matrices so they could look for this in software, and they found, you know, two frequencies that were very reflectionless, one of which went into port 2 and the other didn't, and vice versa. And then they set up the experiment and actually implemented it with two frequencies simultaneously, and it worked. And I won't try to explain this. There's some details obviously here in calibration, but they found 40 dB discrimination for a demultiplexer in terms of going to the right port and not to the other one for each frequency. So it seems like this could be eventually useful in some other, you know, when you make a more practical device. And we also showed, they showed, because I'm just the theorist, that this could do many different routing functions. It could make this one go here, this one go there, that one go there. You could do any kind of reciprocal routing function, because we're not breaking reciprocity here. Okay, so now I'm going to briefly talk about PT symmetry at the end. PT symmetry, some of you may have heard of. It's the idea that if I have a complex potential in quantum mechanics or a complex dielectric function in optics, that if it has this symmetry where when you complex conjugate and do a parity reversal on it, that it comes into itself. So under time reversal, this goes to that, okay? But if I take a half gain and half loss cavity and I do parity and then time reversal, then this thing will come back into itself. Okay. Okay. So we assume we have that. Now let's look what it implies. So the blue is, I guess, loss, and the green is gain, and we're looking at a resonance. Okay. And act with time reversal. So omega goes to omega star, loss goes to gain, and the arrows reverse. Okay, now act with P on top of that, so PT in total, and I now get an incoming state at omega star in the same cavity as I had before, but it's incoming, not outgoing. So this is not invariant under PT, but it maps to the incoming state at omega star. Okay, so resonances of a PT system are mapped to zeros at omega star under this PT symmetry operation. And now, because we've broken T symmetry, we actually can have omega star be real. We have gain and loss, so it's not forbidden. Now, you might think that a half gain, half loss cavity will never laze, but it can laze. Okay. And here's exactly that cavity. As I turn up the difference in loss and gain, these are the poles, these are the zeros. Now let me turn up the loss gain, and should move, yeah. And eventually they meet at the real axis, and you have something we call a CPA laser, okay, which seems almost contradictory. If it's lasing, how can it perfectly absorb? How can you do both at once? Well, remember, the laser's at threshold, so there's no output there, okay? And it'll become, well, maybe I'll tell you here. So remember, it's a two-sided system. There are two scattering modes of the S matrix, two eigenvectors, and one of them is the lasing mode, and the other one is the absorbing mode. So if you send in the absorbing mode to this thing that's just dying to laze, it will not laze, it will actually absorb, but it's dying to laze. So this is exactly what they did in this structure, which I won't have time to go through, but it's got periodic gain and loss here as shown, and there are two different modes that they were able to extract. And then when they excited it at one of the frequencies, okay, they found that for one relative, they have a relative phase shift of pi that's written here somewhere. And so for one relative phase, it amplifies, which it should by a lot, because it's about to laze. But the other, it actually attenuates right where it's highly amplifying. So that's exactly the effect we're looking for. And if they turn up the the pump a little more. Now it'll self-organize to laze without anything coming in, and it does indeed laze at that frequency where it was doing this just below threshold or at threshold. This idea was first proposed by Stefano Longhi, by the way. Okay, so I'm really at the end, so I'll just tell you there's another part here where we apply this PT symmetry and scattering to atoms in a condensate or to quantum particles, okay? And it has to do with the fact that you don't actually need loss and gain to have a PT symmetry transition. I'll skip through this. Maybe I'll just show you a picture. So there's something that had been around for a while due to Carl Bender, that when I have a certain shape of upside down barrier, I could actually get bound states by above barrier reflection. This is amazing, counterintuitive. It's a longer talk. You can ask me about it. But you need the potentials to go to negative infinity to see these bound states. So of course, and they're reflectionless. They knew that they were reflectionless. So we thought, well, let's just truncate this and look for this. And sure enough, we did find it. I don't have time to go through it, but we found we could measure these bound states. That's an example. And we could predict what you would see in an atomic condensate experiment, scattering off a potential like this, which we are told could be done for cold atom condensates. We're collaborating with this group. So I didn't have time to explain it, but it really does predict things that you can measure in atomic condensate scattering. It's just showing that the concept is more general than Maxwell's equations. So I won't skip that. Okay, so thank you for your attention. You see the summary. I don't think I have to say it again. So thank you for your attention.
Okay, thank you very much for the beautiful talk. I'm sure there are further questions. Any questions, anyone? Yeah. Wait a moment.
Hi, thanks for the very nice talk. So there have been these topological lasers. So now this makes me wonder whether you can have something like a topological anti-laser, that you would combine some of those nice features you can have for those, such that you get
right.
Like,
so even the topological laser is about taking a pole and putting it on the real axis by adding gain, and then nonlinear dynamics takes over. So this is completely universal, and the time reverse of that edge state would be perfectly absorbed, if you did everything right. And yeah, I mean that's usually a linear theory. This just works for every linear wave equation, pretty much. So.
Thanks.
More questions? So maybe I have a quick. Yeah, is there a
Can
question?
you over Zoom?
Yes, please.
Okay, great. Thank you. Thank you for the nice talk. I was wondering, when you were talking about the coherent perfect absorption earlier, if it is independent of the wavelength, or does it absorb like a black body, or what is the dependency on the wavelength or the frequency?
Yeah, so that's something I really went too fast on, so I apologize. Thank you for the question. Okay, so we're talking about resonant perfect absorption. The line width is whatever the line width is of the passive resonance. Actually, it's twice the line width, because some of you may know that's what happens when you critically couple. It doubles the line width. So it's narrow band. If you make two of these degenerate, which people here would care about because that's an exceptional point and there are people here working on that, then you would find it's more broadband. And if you made it triply degenerate, it'd even be more broad. But it's not broadband at all, really. It's a resonant process. Does that answer your question?
Thank you.
Okay, very good.
Oh, it's even worse, too. It only absorbs the lasing mode. And people who are looking for perfect absorbers for thermal things or for many other things, they want everything to be absorbed. That means it just can't get out. It goes in and there's no interference. It just is very sticky. You know, it's not an interference effect.
Hey, more questions. I have a quick question. So I don't know whether you mentioned that, but if you break time reversal symmetry by introducing artificial magnetic fields for the photons, does that change the structure?
So that is the topic we're working on at present, but it seems quite resilient, right? I mean, you know, if the asymptotic states are in the magnetic field, then the incoming channels and the outgoing channels will not be time reversed. But you will still, you know, if you take that into account, then there will be these, resonantly absorbed states. And we've done some calculations without doing any brilliant theory yet, and we just get these, and we find them when we put in a non-reciprocal tensor in the electromagnetic simulations. We do get RSMs.
Question?
So you use the symmetry of linear susceptibility basically to phase conjugation. So what if you do the same with nonlinear susceptibilities? Is there something interesting?
Well, as I said, there is a mapping from a laser above threshold to a perfect absorber, with saturation. So, I mean, with saturation, you just have something that doesn't absorb for a weak signal, and then well, it depends if it's overcoupled or undercoupled. If it's undercoupled, meaning it's in the upper half plane, then the nonlinearity would typically reduce the absorption, and then you'll never find coherent perfect absorption. But if it's overcoupled or critically coupled, then critically coupled means for a weak signal you would see it. Undercoupled means that it would not be perfectly absorbing, and as you saturate the absorption, it passes through the real axis, and then it is critically it is perfectly absorbing for some brief interval of parameter, and then it decouples again. So that's the picture. But there are lots of these time. Stefano Longhi has written about time reversing parametric amplifiers and so on. I mean, I think all of this stuff is a possibility to think about now once you open it up. Right.
Very good. So I don't see any further urgent questions at the moment, but I remind everyone that there's food outside and a reception, so there's more possibility to catch the speaker. And now let's thank Doug again.